Assalamu alaikum friends. In this tutorial I will teach you about binary index tree or Fenwick tree. It's basically a data structure proposed by Peter Fenwick in 1994. This data structure is very good at calculating and manipulating cumulative sum of a table of values. If the size of table is n, then using this data structure we can calculate prefix sum and modify the table both in order of log n time, which is very efficient. Binary index tree is used to implement the arithmetic coding algorithm for data compression. Let's first define our problem. Suppose you are given an array of size n having some value at each index of it. That is, frequency of each index is given. Then the possible queries could be add some value to a particular index I of our array and where I lies from 0 to n, and second query could be find cumulative frequency of some index I. The possible straightforward solution could be to store cumulative frequency in some other array, say CF, and then just answer the query of type 2 in just order of 1. But wait, it's not as simple as it seems. Look at the query of type 1. For each query of type 1, we need to update our array. Suppose we had a query to add value 2 to the index 6 of our table array. Then you have to update array CF from index 6 to index 16. Otherwise, you will get wrong answer for every next query of type 2. In worst case, updating will take order of n. But consider a case where size of n is 1 lakh and you are given n queries to answer. Then the worst case could be that all queries are of type 1, and thus this naive approach results in a time complexity of order of n cross m, which is very inefficient. Such a program will definitely give time limit exceeded in any programming competition. Binary index tree can solve this problem with worst case time complexity of order of m cross log n. Range minimum query can also solve this problem with the same time complexity of order of m cross log n, but binary index tree takes less memory and it is very easy to code. Now let's see what data structure Fenwick proposed. Although Fenwick trees are trees in concept, in practice they are implemented using a flat array analogous to implementation of a binary heap. In this data structure, we don't need CF array, so let's delete it. The basic idea of building Fenwick tree is, as each integer can be represented as sum of powers of 2, in the same way cumulative frequency can be represented as sum of sets of subfrequencies. If we consider the index of our array as a vertex of a tree, then the index of a vertex parent or child is calculated through bitwise operations on the binary representation of its index. While building Fenwick tree, we will traverse upward till we find the root. If we are at 1, then we will traverse in this manner till we find the root. And while traversing upward, we will try to add values to each index in such a way that each index will contain the pre-calculated sum of section of our frequency array. And by combining that sum with the section sums, encountered during an upward traversal to the root, the prefix sum or cumulative frequency can be calculated. This will take order of log n in the worst case. Now suppose you are at 1. To move upward from 1, you have to first convert the 1 into binary form. Then look from the extreme right and move towards left till you encounter first 1. Stop there. Now starting from that position till the extreme right, see what is its value in decimal. Here it's 1, here it's 2, here it's 4. To move upward by one step in this tree, you have to add this value to the original value, and by this formula you can do this. Similarly, to move from index 2 to index 4, you have to add this value to this value. We will do this till we encounter the root. While moving upwards, we will add the frequency of 1 to all these indexes. Similarly, for index 2, traversal will be like this. As you can see, this traversal will take order of log n in worst case. For index 3, traversal will be like this. And while traversing upward, we will add the index of 3 to all these positions. For index 4, traversal will be like this. And we will calculate the upward traversal by this formula. After the traversal of our fifth index, the BIT tree will look something similar to this. Traversal from index 9 to index 16 will look something similar to this. We will move upward from index 9 to the root in this manner by using this formula. By using this formula, you will get the decimal equivalent of this highlighted value. After this iteration, our tree will look something similar to this. All these steps which I have shown you can be done in just 6 statements of a C program. Let's see the code now. This block of code will build our Fenwick tree. Now let's see whether this code is building correct Fenwick tree or not by running it. Let's first compile our code. Oops, it seems that there is some error in our code, but don't worry, we will fix it. See, data type of n here is long int, and scanf here is expecting integer value, so this is the error. Now let's see whether it is compiling successfully now or not. I hope it will compile now. Yes, it's compiled. Now let's see the output by running it. In this example, the size of array is 17 and the frequency of each node is 0 1 0 2 1 1 3 0 4 2 5 2 2 3 1 0 2. Let's write it down here. 0 1 0 2 1 1 3 0 4 2 5 2 2 3 1 0 2. Now let's see what is showing. It's showing exactly the same Fenwick tree which we have calculated manually here. Great. Possible queries could be of two types. Type 1 is adding or subtracting some value from an index, and type 2 is finding cumulative sum at some index I. In our program, if k is equal to 1, then k is referring to the type of query. If k is 1, then it refers to query of type 1. If k is 2, then it is referring to query of type 2. Now suppose you encounter a query of type 1, that is to increase the frequency of index 6 by 2. Then you can do this by updating the frequency array in order of 1 by just changing this index from 3 to 5. But you have to update your tree array, Fenwick tree array. But the question is how it should be updated. It's simple. You just traverse upward from index 6 to the last element of your array or root and add 2 to all the intermediate positions which you encountered while traversing upward. Now let's look at the query of type 2. Suppose you are asked to find the cumulative frequency at index 7. Then you will proceed in this manner: 7 minus 1, 6, 6 minus 2, 4, 4 minus 4, 0. Everything will remain same, but instead of adding here, you will do subtraction. This is how you will go downward in your Fenwick tree. And this formula will be used for downward traversal. For calculating cumulative frequency at index 7, you have to declare one variable and then initialize it with 0. Then while traversing downward till you encounter 0, add all the intermediate index values to this variable sum. This is how we will calculate cumulative frequency at index 7. In worst case, finding cumulative frequency at a particular index will take order of log n. So therefore, both the types of queries will take order of log n. Now let's look at the code of doing these steps. Since this is a query of type 2, here is the code. And this is the code for query of type 1, sorry. These 3 lines will update your Fenwick tree, and with these 2 lines we will print the new Fenwick tree in the standard output screen. Now let's see whether our program is giving correct result for these 2 types of queries or not by running it. Let's see what is the cumulative frequency at index 16, 13, 10 and 9. Now let's check whether these are correct or not. Here you can see CF array, which I prepared while explaining to you the name approach, which takes order of n cross m. Obviously this is not present in our data structure, but we can use this for verification. Let's see. At 16, 29, 29, correct. At 13, 26, correct. At 10, 19, correct. At 9, 14, correct. All the results are correct. Now let's look at the query of type 1. Suppose you want to increase the frequency of index 6 by 2. Then the new Fenwick tree would look something like this, and manually also we got the same result. You can check it. It seems that our program is working correctly, so just quit it. Now suppose you are asked to find the sum of frequency from index I to index j. By using the Fenwick tree data structure, you can calculate this very efficiently. Basically, it is asking the sum of an arbitrary subarray. It can be calculated by subtracting the prefix sum before its start point from the prefix sum at its end point, which will take order of n. You can implement the tree data structure in the same frequency array, which will further reduce the memory consumption. But then for finding the frequency of a particular index, you have to subtract cumulative frequency at I-1 from cumulative frequency at I. With slight modification, you can use this data structure for implementing 2D bit. Some of the useful sites for this Fenwick tree data structure are Stack Overflow, Fenwick tree, Wikipedia, Topcoder, and Code Forces. That's all for today. See you guys later. Bye.